Okay, hello and good morning. Welcome to our class. Last week we discussed chapter 5 and we learned how to define the characteristic values of mass, the mass moment of inertia, which we need for rigid bodies when they perform a general motion. And that's what we will discuss today. We will talk about the kinetics of rigid bodies in 2 dimensions. So we simplify our motion to 2-dimensional problems. And first of all, we'll have a look at the script. We will discuss the theory of these type of problems, and then we will start solving different problems. So let's start here. This is our, this over here. This is the script, page 17. There's a question in the chat first regarding the centrifugal moment. The range of x, y, and z depends on the dimension of the rigid body. So you have your coordinate system, and then you have to, your rigid body has a specific length, height, and width, and your coordinates, the range of your coordinates depends on these dimensions. So from your coordinate system in positive and negative direction of the axis until the edge of your object. Okay, let's have a look at the chapter 6.1, dynamic fundamental law of rotation. So this blue line stands for an arbitrary rigid body with a certain mass. And now we want to assume a rotation of this body with respect to, for example, this point right here. Let's call it D. And to describe the motion, the rotational motion of this object, we can simplify our general object to the sum of many objects with known dimensions, known mass, etc. As in statics, as last week in chapter 5, we break it down to simple forms of motion. So in this case, in this general case, we will simply pick a mass point. A mass point over here, dm, and this could be, for example, here. Of course, dm refers to an infinitesimally small mass point, but of course I have to draw it a bit bigger, otherwise you wouldn't see anything. So this is our dm. Okay, and then there's a distance from our axis of rotation to our mass point. Should be a straight line. Here, RD. RD is the distance from the rotational axis, the distance of our mass point to the rotational axis. Was there a question? No. Okay. Okay, now let's assume that our rigid body rotates counterclockwise about the hinge support in D with angular velocity and angular acceleration. Then our mass point rotates about the hinge support as well with radius RD, meaning that it moves along a circular path. It's a point mass performing a circular motion. Then it has two types of acceleration. One component tangential on the path in direction of travel, and the second component in normal direction towards the center of rotation, tangential and normal acceleration. Now we want to describe the loads acting on the system, and we want to be able to describe the moment acting on the system due to the rotational motion. Now we can compute the sum of all moments with respect to the rotational axis. So this is the resulting moment of all acting forces and moments. Of course, in general, there'd be more, could be more loads with respect to the rotational axis. Now, if you have a point mass performing a circular motion, point mass moving along a circular path, we have to consider the inertial forces. And no, it's only one motion. It's not a general motion that we're talking about right now. There's no Coriolis acceleration since there's no relative motion. It's a pure rotational motion. When our point mass is being accelerated in tangential and normal direction, then there's a force, an inertial force acting against the change of motion, meaning that we have to include the inertial forces in our diagram as well. The inertial force opposite to the tangential acceleration, mass times acceleration. In our case, we have the small mass point dm multiplied by tangential acceleration and mass dm times normal acceleration. These are our inertial forces. Okay, now the sum of all forces, the resultant moment of all acting forces is not equal to 0. That's the main difference to our chapter 4 problems. Now we have to consider the inertial forces in our momentum equation as well. Then the sum of all forces with respect to the axis D is unequal to 0. Since we have a rigid body with spatial dimensions, meaning that there's mass that is outside of our point of rotation, our rotational axis, and our system is being accelerated. Now we still have our standard kinematic variables as we discussed in chapter 1 and chapter 2. The velocity of our point mass is equal to radius times angular velocity omega, which is perpendicular to the radius. Then the tangential acceleration can be obtained by radius times angular acceleration, which is also perpendicular to the radius. And the normal acceleration is equal to radius times omega square, pointing towards the center of the circular path, this axis of rotation, as depicted in the figure. Now, for our small mass element, only considering the small mass element, how would the equation of momentum look like? Then there might be external loads, moments, whatever, which are included in this term, the loads that also exist in static systems. And then additionally to our static system, we would have to consider the moment that is caused by the inertial force. And the inertial force is our mass element multiplied by tangential acceleration and then multiplied by the lever arm, which is the radius. So in general, dm at, that's the inertial force, and the radius rd is the lever arm. Force times lever arm is the momentum. And if we integrate this part, we consider the entire rigid body, not just one mass element, but all the tiny mass elements that form our rigid body. And this is 0. Now we can rearrange the equation.
I'm sorry, Professor, why are the arrows of the DMAT and DMAN different to the AT and AN arrows?
What is different?
The arrows, the red arrows of the DMAT and the DMAN. Why are they in the opposite direction of the AN?
That's what we're talking about since a few weeks now. This is an inertial force, and the inertial force acts against the change in motion, meaning that it always acts opposite to the acceleration. When I accelerate an object, then I change its current form of motion. It changes in speed and or it changes in direction, depending on the type of acceleration. So I changed the motion of the object. It's not a static system anymore since it's being accelerated, and the inertial force acts against this change of motion. And that's why it always points opposite to the acceleration.
Okay, thank you, Professor.
Yep, you're welcome. Yes, green are the accelerations. They are our kinematic variables, and red are forces.
Excuse me, Professor.
Yes.
Why do we integrate the formula?
Because dm is just our one mass point, our tiny infinitesimal small mass element, but our rigid body consists of all the mass elements added together. And then if I integrate, I obtain the entire system. So of course, otherwise I wouldn't be able to draw the system, draw the figure. But in reality, what we assume is that there are a whole lot of boxes sitting next to each other. like this, more or less. The idea is not different to chapter 4. It's still the same idea. It's the same method, same approach. Of course, it cannot be different. What is new here, that we are not considering a point mass, a single mass, moving, performing a general motion, but now we have a rigid body, not a point, but a rigid body with spatial dimensions. And this rigid body can rotate and has an inertial moment as well. The point mass cannot rotate about its own axis. We would not see this. We would not be able to describe it since it has no spatial dimensions. Well, yeah, the radius is just a general variable here. It's not, we have to apply the radius to all our masses. That's why the radius is inside the integral as well. I'll rearrange the equation, then maybe it's easier to understand, easier to see. I substitute the tangential acceleration by this equation right here, RD times alpha. Okay, I substitute this into our equation. Alpha is a constant. And then we do not have to integrate over alpha, but as you just asked, our radius is dependent on the position, dependent on the mass element under consideration, and the position and size of the mass element under consideration. And that's why we have to integrate over the radius. And that's how we consider it, the different position.
Okay, thank you.
Yep, you're welcome. Okay, now the second part of this equation should be familiar right here. This is our mass moment of inertia. That's the equation of the mass moment of inertia that we just discussed and talked about last week. No, it's a general integral. That's why there are no dimensions, because it's a general object. We are deriving our equations for a general system. There is no specific length, height, and width. Okay, so what we stated last week was that JD is equal to the integral of r square dm, integration of the square of the radius over the mass. And I'll state it here again. This is our mass moment of inertia. And what we are doing in this integral, we compute the mass moment of inertia using the distance RD of each mass point. dm to the rotational axis. And of course, we do not want to integrate this equation every time for every rigid body that we are describing. But we do know a simplification of this equation, because we know that the mass moment of inertia with respect to a general axis of rotation, our axis d, can be derived by the mass moment of inertia of the center of gravity of the system plus the Steiner share, E square times m. And E is the distance of the center of gravity of our entire object, of our rigid body, to the rotational axis. The distance from the center of gravity to the axis of rotation, D. Alpha is constant. Alpha is not dependent on the position. The angular acceleration is has the same value over the entire rigid body. That's why we do not have to integrate over alpha. It can be outside of the integration. Okay, again, JD, the mass moment of inertia of a general axis, can be computed by the mass moment of the center of gravity plus Steiner share. Yes.
Professor, what is E in this case?
E, as last week, it's the same. It's the distance from the center of gravity to the axis of rotation.
Okay.
C, center of gravity, and D, our current axis of rotation.
Right.
The radius that we used for the simple example, or this example we did, 5.1 was the first example where we used it. JC is the mass moment of inertia of the center of gravity of the object. Another question? Oh.
Professor,
Yes.
how did sum of moment around point D became alpha integral of R squared D?
I substituted this AT, tangential acceleration, by R times alpha.
Yeah, then how did it become R squared?
Because there is one R already, and if I multiply by R, it becomes R squared.
Yeah. Okay.
Okay.
Professor, another question. In this case, E is CD, but we are taking all the point masses, right? So how do we integrate E as well then?
No, E is, we do know the center of gravity of our entire system before we integrate. So E is our, for example, in this example, in this simple case here, the center of gravity might be here.
Okay.
I don't know, probably not, but could be here. And then E is the distance from C to D, the absolute distance, and the absolute mass multiplied by the entire mass of the system.
Okay. Okay. Thank you.
Yeah, you're welcome. Okay. Now we substitute this mass moment of inertia into the equation above, into the equation of the momentum. Then it says sum of all moments with respect to the rotational axis of D. In general, this could be time dependent, since alpha could be a time dependent variable. Alpha could change over time in general. In our cases, we usually simplify our problems assuming a constant angular acceleration.
Yeah, Professor, I have a question.
Yes.
Yeah, we say the summation of moment is equals to alpha times the integral of RD squared dm, right?
Yes.
Okay. Is it? Are we trying to make an analogy to JD? Like, okay, JD is also equal to the integral of.
Well, it's not an analogy. It's just it's a fact. JD is this, what's stated in this orange box here, and we just derived that the mass moment of inertia, that the sum of all moments is equal to the mass moment of inertia multiplied by the angular acceleration.
Okay. Okay. So we just use the standard formula for JD. Okay.
Exactly.
Okay. Yeah.
Prof, one question.
Yes.
You said this formula, the last one we just generated, where we brought out the moment of inertia, here. You made a statement concerning constant angular acceleration.
Yes.
Whereby we have a body consisting of varying acceleration. Will these formulas still be applicable?
Well, yes, this is the general formula, assuming a time-dependent acceleration, assuming that the angular acceleration changes over time. But what I said is that in most cases, we can simplify this equation by neglecting the time dependency, assuming that A does not depend on time. But here, we do have the time dependence in the equation.
Okay, thank you, Prof.
Yep. Okay, so the equation that is stated here is our dynamic fundamental law of rotation. In case of rigid bodies. So we do have to keep this simplification. If our body would not be rigid, then the mass moment of inertia would also be time dependent. Okay, so in general, assuming non-rigid objects, the mass moment of inertia would not be constant. But again, it's important to know, but in our class, we are only considering rigid bodies. We do not consider non-rigid objects, okay?
Professor, non-rigid objects like point mass, right?
No, a point mass is not an object. It's just a point without spatial dimensions. I'm referring to objects that change in shape during the motion, that deform. A beam that is bending, for example, changing its length, something like that. Okay, so this is our additional equation, our dynamic fundamental law of rotation for rigid bodies performing a pure rotational motion. Then we can also consider this motion, we have to consider this motion and the kinetic energy of the system. So our equation for the kinetic energy in case of a rotating body becomes, well, we'll state it for point mass first, or for our tiny mass element. Then we would have this component of kinetic energy, which is equal to 1/2 mass, dm in this case, multiplied by the square of the velocity. That's the kinetic energy you know and that you use for point mass as well, 1/2 mv². In our case, the mass is this small mass element dm, and our velocity in case of a point mass performing or moving along a circular path can be described by r times omega square. And now, when we consider the entire object, we have to integrate over the kinetic energy. And then we have 1/2 r square omega square dm. And again, our angular velocity, omega, doesn't change when considering different mass elements. The angular velocity, as the angular acceleration as well, has the same value in the entire object. Independent, it's independent on the position. We do not have to integrate over omega. We only have to integrate alpha, and I think you see where this is going. The integral corresponds to our mass moment of inertia again. And of course, in general, it's time dependent. Now again, for a translational motion, or the motion, general motion of a point mass, kinetic energy is equal to 1/2 mass times square of velocity. In case of rotational motion of a rigid body, the kinetic energy is equal to 1/2 times mass moment of inertia times square of angular velocity. Okay, let's solve a first example. Applying
Professor,
the equation. Yes.
Before then, yeah, you said for general, the kinetic energy for general motion
Of a point mass.
of a point, okay, of a point mass, yeah, it's going to be the half of the mass times the velocity square.
Yes, square. Yes.
Okay, this velocity would be the
absolute
leading,
velocity
the
of
absolute
the point
velocity
mass.
that we
Yeah.
calculate. Okay.
Yes. So it could be the velocity due to translation or due to circular motion, or if it's a general motion, then the absolute velocity of this motion. Okay. So let's have a look at the first exercise, exercise 6.3. Okay, and there it is. Okay, what do we have? We have a drum dryer that is driven by an electromotor over a chain drive. And the mass moment of inertia of the drum is given with 20 kilogram times square meter. And the mass moment of inertia of the motor is given as well, 0.1 kilogram times square meter. And then we have a ratio of the chain wheel diameter from drum to motor, which is also given. And the motor is accelerating the drum using a constant torque of 50 Newton meter. And we have to find the time that is needed for the drum dryer to reach its nominal speed of 250 rounds per minute. And the system starts from standstill. So it's not moving. Then the motor applies the the constant torque, and over the chain drive, the drum starts to rotate, it accelerates, and until it reaches a nominal speed of 250 rounds per minute. The question is, how long does it take to reach this nominal speed? Okay, how to approach this kind of problem? We have a mass moment of inertia given, we have a torque given, so this indicates that we have to apply forces and loads to the system. Then if we are doing that, we have to free our subsystems, our individual masses, the drum and the motor in this case. So let's start. This is our drum, and that's the motor. These are our rigid masses. And I will integrate the chain as well. Of course, we had to cut through the chain and through the support. Okay, and now we draw, we add all the forces, all the loads acting on the system. Then, first of all, we see the support reactions. Let's call them A and B, A vertical and A horizontal, and B vertical and B horizontal. When we free the system from a support, we have to include the support reactions, even though we are not interested in the support reactions in this case right here. But they are part of our free body diagram. Now, we see the tension in the chain. Have to consider axio equals reactio. I'll call it F1 for the upper chain and F2 for the lower chain.
Excuse me, Professor.
Yes.
Speaking of support relation, I thought we will also put the support relation on the floor.
We do not see the floor. I did free the drum and the motor.
Okay.
And they are mounted in the support and not on the ground.
Okay. Okay, thank you.
Yep, okay. Now, before we can include the inertial moment, we have to consider the motion. Now, the torque of the motor is given with this direction, mm. Then we do know the direction of rotation, the direction of motion of the system. This would be the angular velocity and angular acceleration of the motor. Then the chain moves to the left in the upper part. And then on the drum, we have omega t and alpha t, angular acceleration and velocity of the drum. And then the chain moves to the right on the lower part. Now the mass moment of inertia are given, and this indicates that our drum and the motor itself do have a mass that we need to consider in our computations. And due to the mass, they have an inertial moment that is acting against the change of motion, our J times alpha. Same as for the inertial forces in chapter 4. Our inertial load acts against the change in motion. The inertial force acts opposite to the acceleration, A, and our inertial moment acts opposite to the angular acceleration, alpha. Meaning that we have an inertial moment here, jt times alpha t, and an inertial moment on the motor, jm alpha m. Okay, and this is our free body diagram.
Excuse me, Prof.
Yes.
Is it a principle that the moment of inertia, the direction of the moment of inertia moves opposite to the direction of motion?
Opposite to the direction of alpha. Yes.
Okay, okay.
Okay. Now, how many unknowns are there in our system? We do not know the angular accelerations of drum and motor, alpha t and alpha m. So these are two unknowns. We do not know the tension in the chain, F1 and F2, which are also two unknowns. But of course, we are not interested in them, and we could sum them to one, F1 plus F2, for example. And we do not know the support reactions. We are not interested in the support reactions. Then when building the equilibrium conditions, we shouldn't build the sum of all forces, because this would just give us additional unknowns, which we don't know, which we don't need, which we're not interested in. So it makes no sense to state these equilibrium conditions. Then we should only state the sum of the we should only state the equation for the resulting moment, sum of all moments with respect to the center of rotation in this case. Then we have two equations there. We still need a third equation, and the third equation is our kinematic condition, a relation between the motions of the left subsystem and the right subsystem, our two kinetic variables. This is what we have to do first before solving for the loads. First, we have to discuss kinematics.
Okay, Professor, I have a question.
Yes.
If we are not interested in the support reaction, why do we have to show it in the free body diagram?
Because they are there. We cannot neglect them. They are there. I'm also not interested in the tension in the chain, but I do have to consider them. Otherwise, my system would not be complete.
Okay, just for the sake of completeness, that is.
Yeah, because they exist. If I would build, if I would neglect them in the diagram and then I would build the equilibrium condition, it would be wrong. The equation would be wrong because there are forces missing. Okay. So we do have to draw all the loads that exist in our system.
Okay, but then when stating the equation, we just can just neglect them.
Well, no, I'm not stating the equation because what I want to do is I only want to build the equation of momentum with respect to A and B. Then I do not see the support reactions simply because I'm not using the equation where they appear. But of course I could, if I do not know how to approach the system, or when I'm unsure how to approach the system, what I would usually do is, and what you will probably do as well, is you draw your free body diagram and then you state all the three equations that are possible. State these three equations and then try to solve the system. And this works. And you will obtain a solution, the correct solution. But you will only obtain the correct solution if you have a complete free body diagram. If not, you'll get a wrong result.
Okay, let's continue. Maybe along the line, I will get you understand it along the line.
Okay, so
Professor, I'm
yes.
really sorry. Just quick question.
Yes.
Can't we, since even though we don't consider the forces, couldn't we state that F1 equals F2 from the very beginning?
No, they
Because
are not. They are not
they are
of same
not?
size. No.
Why?
Just take the second subsystem, this one right here.
Yes, I see.
Oh.
From the sum of forces.
Yes.
Mm-hmm. Okay.
That's really important. We had the simple system with the how was it, like this somehow, I think. Remember, something like this. This exercise. And here, these pulleys were massless. We assumed the mass to be 0. And only when the masses of the pulleys, of the wheels, or whatever, drum and a motor in this case, are 0, then the tensions are of same size on left and right side of the system. In this case, F1 and F2. Only if the pulleys or wheels or whatever are massless. When they do have a mass, the tension is different. They are not of same size anymore. Okay, that's really important to remember.
Yes, and even though in the problem there was no statement about masses, there was a statement about mass moment of inertia, so we cannot consider these drums massless.
Exactly, because the mass moment of inertia is obtained by r squared dm. So the mass moment of inertia can only exist if the system has a mass. If the mass would be 0, there wouldn't be a mass moment of inertia. Okay, kinematics. We do have to find a relation between our left and our right subsystem. So our kinematic variables are either distance, velocity, or acceleration. So maybe we could state it for velocities here. The velocity of the chain drive, V, is equal to the angular velocity of the motor and the drum. For the motor, there would be, sorry, not phi. It would be omega m times Rm. And for the drum, it's omega t times RT. The chain has the same speed everywhere in our system.
Professor, that's the tangential velocity, why?
Well, yeah, on the drum and the motor. That's the velocity of the chain in any position on the drum or motor, which is always tangential on the circular path.
Okay.
Yeah. Okay, now we do not have the radius given. The diameter is given of drum and motor. And that's why I will rearrange this equation using the diameter, omega m times dm over 2 is equal to omega t dt over 2. And now I rearrange the equation to dt over the m diameter of the drum over diameter of the motor, which is equal to omega m over omega t. And this ratio is given in the problem description. This is I, which is 3.8. And this is my kinematic condition. A relation between two kinematic variables. So it's omega m is equal to I times omega t. And if this condition is true for the angular velocities, it is also true for the angular accelerations. Alpha m is I times alpha t. Okay. And now I can start with the kinetic computations. And for the kinetic computations, I will build the sum of the momentum, all moments, with respect to the axis of rotation. So for the motor, I would build the equation with respect to the support in B. And then I have 0 is equal to F1 times dm over 2 minus F2 dm over 2 plus torque of the motor and minus Jm alpha m. So that's equation number 1. And then for the second equation, I built the sum of all moments with respect to the support in A. 0 is equal to F2 dt over 2 minus F1 dt over 2 minus Jt alpha t. And that's equation number 2. Now I'm interested in the acceleration, and I'm not interested in the tension of the chain. Then I rearrange one of the equations for the tension F1 and F2 and substitute this equation into the second equation. And for example, I could rearrange equation number 1 to F2 minus F1 is equal to mm minus Jm alpha m 2 over dm. Which moment about the drum? This is the equation of momentum about the drum, and there are only the tensions in the chain and the inertial moment. This one right here. There's no driving moment. The drum is driven due to the motor on the right and the chain that is connecting drum to motor. There's no additional moment. There's nothing else in our free body diagram. Okay, then let's substitute this into equation number 2. And then we have 0 is equal to minus Jm alpha m 2 over dm dt over 2 minus jt alpha t. The 2 cancels. Then dt over dm is I. And this gives I times minus alpha m, oops, is I times alpha t. And this is I squared Jm alpha t minus jt alpha t. And now we can solve this equation for the angular acceleration of the drum. Like this. All these values are given. And then when we enter these values, the given values, into the equation, we obtain 8.86 per square second. Okay. And then we can also compute the angular acceleration of the motor by I times alpha t, which is 33.67 per square second. Both accelerations are constant since the driving torque of the motor is constant, and we obtain values, so specific values, so they have to be constant. And then we can integrate to obtain the angular velocity. So if we do that, we integrate the angular acceleration of the motor. In general, it would be omega t0 times plus alpha t times t. And since we know that the system starts from rest position, the initial angular velocity is equal to 0. And from here, we can compute the time that is needed to reach the nominal speed. omega, the angular velocity, is equal to 2 pi n over alpha t, and the nominal speed is given with 250 per minute. Then we have to convert it into seconds. Then this is 2 pi times 250 over 60 seconds divided by 8.86 per square second, and this is 2.95 seconds. Okay. Any questions?
Yes, I have a question. It's rather a general question. I'm a bit confused about the COEs when we write them. For example, if you scroll a bit up. So yeah, for in the first equation or the second one, we equated them to 0, which
Yes.
made sense in statics, but I'm still confused. Like I'm always confused during mechanics or dynamics when we have a motion. Why do we set it to 0 then? Like there has to be some result,
Yes.
Net resultant, right?
Yes, it's not 0. It's equal to this. It's equal to the inertial moment and equal to the inertial force when we build the sum of all forces. That's the main difference to statics. We have these inertial loads in our system. And considering the inertial loads, the dynamic equilibrium can be set to 0 as well. So that's what we stated in chapter 4 at the beginning, that we said the sum of all forces, well, I neglect the time dependence maybe. In statics, we would have said this is equal to 0. Yeah, this would have been statics. And in dynamics, this is not 0 anymore.
Yeah.
It's not 0 in dynamics, because what it is this additional load in our system, m times a,
Yes.
equal to the inertial force. That's what we are stating for the sum of all forces. And of course, for the sum of all moments, we are stating this as well, because now that's what we just discussed in the theory part. We say, okay, the sum of all moments with respect to the rotational axis is also not 0 anymore. It's unequal 0. It's JD times alpha.
Okay, and then we write it in a way that like we take it, subtract it from the other side of the equation.
Exactly. We simply rearrange the equation.
Bit. Okay. Oh, yes.
And that's why we have this minus sign here, because we say it's always acting against the change of motion, against alpha. And that's why it's negative in our equation. And then it equals to 0. The same here as well.
Excuse me, Professor.
Okay. Thank you.
Yeah, okay.
Professor?
Yes.
The equation on the left is Newton's second law, right?
Which equation?
F is equal to ma.
F is, oh, here.
Yes.
This is Newton and this is Newton.
So D'Alembert just rearranged the equation and got it named after him.
Yes, I just rearranged and put this over there.
Okay. Very nice.
Yeah. Was there another question? Okay. If not, then of course this was a simple type of motion. It was a pure rotational motion. We already discussed the other simple form of motion, translational motion, since it's similar to our motion of a point mass. we already discussed this in chapter 4. There's another question in the chat. How did I get which equation? This one?
Yes, Professor.
I simply integrated alpha, or if I don't remember how to integrate alpha, I have a look at the first page of the formulary and use this equation right here. Circular motion, alpha being constant, leads me to this equation for omega. Okay.
Okay, thank you, Professor.
Yep. Okay.
Professor,
Yes.
how do we integrate alpha if it is constant?
Well, how I'm just integrating a constant over time. If I integrate a constant over time,
Oh yeah, I see.
it's simply this. Okay.
Okay, thank you.
Yep. Okay, now if there are no more questions, let's go back to the script and talk about the next script. Let's talk about the next subchapter 6.2, the inertial forces and moments in case of rotation. Right now, we only discussed the inertial moment with respect to the general axis of D. And of course, we already mentioned that we do have to consider the inertial forces as well. And that's just the equation that is stated here again, the equation you know from chapter 4 already. It is also true and also has to be used for rigid bodies as well. And we have to consider the eccentricity. Same as before, if our object rotates about a general axis D, we need to define the distance from the center of gravity to the current axis of rotation. And simply due to that, we have to consider the tangential and normal component of the acceleration, which gives us two inertial forces, one tangential and one in normal direction. And additionally, this equation right here, the equation of momentum, as stated as on the previous page. Now, we already talked about this. Here it is written again. We use principle of D'Alembert to solve the system, meaning we use the same approach as in statics. Only difference to statics is that we have to consider the inertial loads in the system. Okay, so what are our additional loads that we have to consider? I will just repeat that what we did in chapter 4 and 6, such that we have it incomplete or all complete here. We say that our object moves translational. That's the sentence we stated in kinematics. Simply that now we are interpreting it using forces. The body moves translational with the velocity of the center of gravity being E times omega, tangential acceleration E times alpha, and normal acceleration E times omega squared. E as stated above. Distance to our axis of rotation. So now our body moves translational with these variables as the center of gravity of the body. Our second point. Then this leads to the inertial forces in the center of gravity. That's important to know, important to remember. Inertial forces only act in the center of gravity, nowhere else, not in edges or additional supports or whatever, only in the center of gravity. Oops. Inertial. Then we have two additional forces compared to our static system. Two additional forces acting in the center of gravity, minus ME alpha and minus ME omega square, minus since they act opposite to alpha. And additional to the translational component of the moment, our object rotates about the center of gravity. Okay, and this results in the inertial moment. That's what we have to do if you have a rigid object rotating about an eccentrical axis, an axis that does not correspond to an axis passing through the center of gravity. Since the support causing the rotational motion also needs to absorb dynamic forces. Now, in case of a rotational motion about an eccentrical axis, we have to consider the arbitrary dynamic equilibrium condition. We can state the arbitrary dynamic equilibrium conditions, sum of all forces in tangential and normal direction, including the inertial forces, and the sum of all moments with respect to our current axis of rotation. And then we have two components here, the inertial moment with respect to the center of gravity and the Steiner share, which is a result of the tangential inertial force. And again, in this kind of motion, we have to consider kinetic energy using this equation right here, being derived as on the previous page.
Professor, when the axes don't pass through the center of gravity, we have the centrifugal something, right? Moment or whatever.
The inertial force. We have to consider the inertial force.
So is that the centrifugal thing, which JXY or something like that? Which is
the Coriolis acceleration, is that what you mean?
No, the one which we did last time when we did J, there was something
yeah.
called
We said
JXY centrifugal.
JD is equal to JC plus E square M.
So E square M is the Steiner share, right?
That's the Steiner share. Yeah.
Yes, but there was something called JXY or something like that.
Oh, yeah. Okay. No. This in our case, this is 0 because we place our initial coordinate system into the center of gravity and assume them to be our main axis. So what we have to do is, the only thing we have to do is use the parallel shifted axis of rotation, applying Steiner share, or a second option would be the rotation, or a combination of both. But as long as we start out with our main axis, this part right here, the initial mass moments of inertia, centrifugal moment, they are 0.
Okay.
Then there might be a J-ax Y star, but that's usually not relevant in our cases.
Thank you.
Yep. Okay. Okay. This is the how the equations would look like in case of a pure rotational motion about an asymmetrical axis. Now, as a last step, and before we start solving a whole lot of exercises, we will make the step to the general motion. And once we're able to describe the general motion, we can always simplify this general motion to the specific types that we discussed so far. So if we move one page further, we have chapter 6.3, general motion. And what I will state here is very similar to what we just stated for this case of rotation about an axis D. Then again, we use the same approach as for the kinematics of a rigid body, superposition of translation and rotation. Now we assume that our body moves translational with VC and AC as the center of gravity. They are vectors now, since they can point in any direction in our plane of motion. And then we have the inertial force in the center of gravity acting opposite to the acceleration of the center of gravity. So in general, it's minus MAC. And at the same time, our object rotates about the center of gravity. Which gives the inertial moment. Minus JC times alpha. So very similar to what we just stated before. But this is the general approach, and then which leads to our general dynamic equilibrium conditions, similar as the ones on the previous page. Our acceleration is a vector, then it might have a horizontal and a vertical component. And then there's only the inertial moment with respect to the center of gravity. Okay, and okay, the equation for the kinetic energy as well. And here also the velocity might consist of two components. And then this general approach simplifies depending on the specific situation. And here are 5 special cases, special situations. First one would be a static system. In case of a static system, all the accelerations are 0. Of course, then the second part of all these equations of the dynamic equilibrium conditions vanishes if the acceleration is 0. Then the second special situation would be a point kinetics problem. A point mass has no spatial dimensions, and if there are no spatial dimensions, the mass moment of inertia is equal to 0, since the radius would be equal to 0. R squared dm in a point mass, R would be 0, since there are no spatial dimensions. Third option is a pure translational motion. Then our rotational values are equal to 0, meaning angular velocity and angular acceleration would be equal to 0. And of course, we could have a pure rotation about the center of gravity. Then our inertial forces would vanish. Since there are only inertial forces acting in the center of gravity, and if the center of gravity doesn't move, then there's no inertial force, since the acceleration of the center of gravity and the velocity as well, of course, are equal to 0. And last option, we might have a rotation about the eccentrical axis, what we discussed on the previous page. Then we have to consider tangential and normal component of the acceleration, depending on the distance, on the eccentricity E, distance from our center of gravity to the axis of rotation. Okay. And that's it. That's all we need to know for chapter 6. But of course, I think you can imagine there's high variety of different problems that we need to discuss. Well, at least 4 of these special cases we will not consider static systems. So we will spend the next weeks solving problems, and of course will be time for you to practice these type of problems and discuss them in class. Okay, any questions so far? If not, then I would like to stop here for today, and on Friday we will start solving problems. Then if there are some questions that you want to discuss in consultation hour that you have prepared maybe, then you can do that right now after class, and if not, then I wish you a good week, and we continue here on Friday. Bye.
Thank you, Professor.
Yep, you're welcome.
Yes, Professor, I have a couple.
Yep.
First of all, can you please remind me, you always saying in the very beginning of every problem that since we're giving, for example, mass moment of inertia, this is saying that we need to use this kind of equation, this kind of approach, or if we're giving, I don't know, the height, we need to use the energy conservation law, because I'm afraid that when the exam comes, this will be a real problem to understand which approach I need to use.
Well, in the exam, there's usually help giving for all the problems because you have different questions for every exam problem, question A, B, and C, or whatever. And then there's a drawing, and you usually there's a drawing given, and you have to complete the drawing applying velocities or loads or something like that. So the first thing would be to read the problem carefully, because if the question asks you to, or the task asks you to draw all velocities acting on the system, then it's probably a kinematics problem. And if you're asked to draw loads, then it's probably a kinetics problem, forces. This is usually stated in the exam. So so you need to read carefully.
Okay.
Then
I understand.
Yeah. Then usually if you have a system consisting of several masses that are connected by a rope or something like that, then you will need kinematic conditions. But this is also asked for. Usually then in these type of problems, part A is state the kinematic conditions or something like that. And for energy problems, then it's usually something, it usually has something to do with work being applied or extracted, or consider the frictional work or something like that. So usually, but it's really important that you read the text, because in the text you have all these hints to what you have to do. So not just have a look at the figure, because then of course there might be options, kinetics or kinematics or something like that, but read the text quite carefully. And yeah, whether it's a point mass or a rigid body, if it has spatial dimensions, then it's a rigid body, especially if these dimensions are given, and or a mass moment of inertia is something like that, then you should use that approach. Also, for example, if you think of the robot arm problem, that's a problem that you can solve using both options, point mass or a rigid body. But in case of a point mass, if you would solve this problem as a point mass problem, then the figure given would be this. And then you would draw your leading and relative vectors in the same point. If it would be a rigid body problem, then you would probably have something like this. Also, if you have something like this, you will probably need to include loads, forces, and moments, something like that. So I think maybe if you try to solve problems on your own, then just try to think about what it might be, what approaches you have, because actually there are not that many different approaches.
Yeah, that's the point, because all the problems are divided by the sections, that the parts that we're going through. And I know that this problem includes the kinematic, and this problem includes mass momentum of inertia, and this includes kinetics. That's what I was asking for, but
okay, yeah,
you have already completely answered it. Yeah, and
perfect.
just one really quick question regarding the problem, and I will go. I have prepared it, and I just wanted to.
You want to share?
Yes, I want to share.
Okay.
And I wanted to ask if my thought process is correct.
Yes.
This is a problem number. Just give me a second. I'm trying to find it. This is the problem 4.7.
Yeah.
And I'm stating that A1 plus A2 is equals to A3. And I'm stating it from the fact that S1 plus 2S2 plus S3 is equals the ST. And when I take the derivative, I will receive a velocity. And
if you integrate.
Yeah.
Oh yeah, from the distance. Okay. Yes.
From the distance, yeah. And this is the point that I'm trying to discuss. the velocity should have a reference point, and this is important. And I'm saying that reference point is when these two pulleys on the top. This is
Yes.
my reference point.
Mm.
And from this reference point, I'm stating that V1 is positive and V2 is positive, and V3, since it's going far from this, is negative. And all the sign convention comes from this reference point that I'm stating.
No.
Okay.
In your first equation, the ST on the right-hand side of the equation,
Yes.
what is it?
It is the total length of the rope.
Okay. But the total length of the rope doesn't change by the distance traveled. You have to think of the distance the rope travels. And so the distance the rope S1, the part S1 travels downward, and S3 travels, no, what is it? S2 travels downward.
They are a bit mixed, but yeah, S2 should be going downwards. I mean, I'm saying that this is
Yeah,
S2.
S2. Yeah, okay.
Yeah, this will be S3.
Then S1 plus S2 is equal to 2 times S3. The distance the rope travels above the upper pulleys,
yes,
sums up to the distance the rope travels on the lower pulleys, or the mass M3 travels.
Okay. Okay, I see.
And then you can build the time derivatives correctly.
Mm-hmm. Now I see. Okay. No, I got the right answer, even though I didn't get this right thing. Okay.
Okay.
Yes, thank you. That's all.
Yeah. Okay. You're welcome.
Professor?
Yes.
We have a question in 3.13.
In 3.13. Okay. What's your question? You want to share the screen or?
No. We don't have a. I mean, we can take a picture of it. But
that's the bike 3.13. Oh wait. Oh, the motorcycle. Yeah, just the first two parts of the motorcycle problem can be solved applying what we learned, but please don't solve the third part. It's just they are making an assumption that doesn't really make much sense. So maybe just neglect this problem.
Is the assumption about FF by any chance?
Yes, about the force.
Yes. Okay. Okay, Professor. That was the question.
Yeah, exactly. Because it doesn't really make sense. So just neglect this exercise.
Okay. Thank you.
Thank you, Professor.
Yeah, you're welcome. Okay. Further questions? Okay, well, if not, then I will stop here, and maybe there are further questions next week. Or
we have
yeah,
one more.
Okay.
So 3.11. So it was about. Yeah. So in the last part. So A part.
The person, the bungee jumper.
Yes.
Yes. So
Yes. Part B or
part A or B?
A?
Part A. Can we take any reference? Like, can we take the topmost position as the reference point and solve it?
Yes, you can. It cancels the additional length or the additional potential energy you might have on one side, because it's not there on the other. So you can either pick the point on top, or maybe the depicted position when the person is furthest down. would also work. Both is possible.
But then the top part will become 0, right? Because
Then
that is
yes, exactly. Then there's a 0 on your left-hand side of the equation.
But then it turns into a very complicated quadratic equation.
It turns into a quadratic equation independent on your reference point. But it's not a complicated. It's you have the length delta L.
Yes.
Quadratic for delta L, right?
Yes. Yes.
And then you only have to solve your quadratic equation, PQ formula. You know how to solve a quadratic equation?
Which formula?
It's probably called PQ.
I'm getting. Can you share your screen?
Well, yeah, but I don't have the problem here.
Yes,
So,
I have the problem.
But then you share the screen, or
Okay.
I'll just
Yeah.
Oh yeah, this is the page. Okay.
Yes, and the equation that I'm getting is delta L1 is equal to half C delta L1 square minus MGL minus 2 MGS upon MG. So now we solve for delta L, right?
No, yeah, you should have something like minus 1/2 C delta L square plus MG delta L plus MG 2S plus L. Maybe you probably rearranged it differently.
Yes. I'm getting MGL, not delta L. No, you're right. Yes.
Here's the MGL part is done.
Yes.
Yeah.
And so how do you solve this quadratic equation?
Well, first of all, you have to rearrange into something like delta L square plus, I just call it A, delta L mg over minus 1/2 C plus B. Okay?
Yeah.
And then you solve for delta L. Delta L, there are two solutions, is equal to then minus A half plus minus square root of A over 2 square minus B. That's how you solve a quadratic equation.
This is negative.
If you Google PQ formula.
Yes, but Professor, we tried this. It turned out to be imaginary. I don't know how.
Well, then you have a problem with your signs. It will be imaginary if this is negative.
Yes. But then we use the other approach that you taught us, which involved iteration, I think.
Yeah. Okay.
And it was
we got
the answer. So is that also fine?
This is also fine. Yes,
is
of course.
Is that valid?
But yes, that's valid. But this would be faster. So you probably have a problem with your numbers. Some sign is wrong or something like that. Because if you divide by minus here, then A would be negative and B would be negative, and B minus 1 turns into a positive value.
Professor, is this the formula, quadratic formula, minus B plus or minus B squared minus 4AC by 2A?
Yes.
Yeah.
Okay, Professor. Thank you.
Yeah. Okay.
Yeah, thank you.
You're welcome. Okay. Any further questions? Then if not, let's stop here for today. And then we continue with our class on Friday, and next Monday there will be time for questions again. Then have a good week. Bye.
Bye. Thank you.